Okay, in this video, I'll walk you through how we will leverage HyperStudy to calibrate the input parameters of a PM FlexTire model so that we can match the force deformation response and rolling resistance. The first thing that we will do here is add in a parameterized model. I'm going to change the name of this parameterized file to FXT file, leave it as model 1, and we will select in resources here the model that we need to parameterize. In this case, we're going to parameterize the FXT file. This FXT file is used to pass the input parameters to the PM FlexTire solver. I'll click yes because we need to set up a parameterized model for this. The structure of the file is in such a way that we have a header. I would expect that you wouldn't have to change that. The units are provided here. These units are how the input parameters within the file are interpreted. So you don't have to match these units to SI units or to the units that you're using in EDEM. You can specify the units that you will use that will be used to interpret the inputs in the file. In this case, I don't think you have to change anything with the rim. I've set the mass to 120 kilograms. Note that there's two places that will input the mass of the tire. One is in this FXT file, the other is in the EDEM GUI. And we'll, for now, neglect the bead input. The parameters that we do want to change are associated with the material and the material inner liner, belt, and sidewall. I've also specified here a 16 psi or a 110,316 Pascal pressure that is going to be inflated between 0 and 0.1 second. So the way that the solver is set up for PM FlexTire, you can operate in a number of different modes. In this case, I'll be demonstrating the simplest with a material type set to 0. That means that we're assuming that the material properties are isotropic. All the materials are the same in every direction. So that means that just the first three inputs taken from the sidewall, belt, and liner will be used. So E mod, Poisson, and thickness, E mod, Poisson, thickness, E mod, Poisson, thickness, and the material. Always all three of those are used. Now the material input is used for the carcass of the tire, and then our individual subsections are associated with the flag. We've got an inner liner, so that's the surface that air pressure is applied to. We have the belt, which is generally the band of material that's down the kind of center of the tire. We have the sidewall as well. So what we need to do to create a parameterized file here is to select the string and select create. In this case, I'm going to name them material underscore emod, and I'll set the label and the variable name the same, and then I'll repeat that for all the other parameters that we'll include in the parameterized file. Okay, we've defined all of the parameterized inputs that we want for this file. We'll click OK, and we'll save this in the root directory, and we'll call this the tractor tire. We can go ahead and import the variables, and then we'll see that we have the list of all of the input parameters that we're taking from the FXT file. We're also going to change the extension of this to FXT because that's what we want is the output after the parameterized file is updated. And you'll see here that we have some cells that are highlighted. That means that the nominal is outside of the upper and lower bounds. I'm going to go ahead and update the bounds to a reasonable level. So here I've updated the upper and lower bounds. We can proceed through, write and execute this model and have a look in the directory. Within approaches, setup, run one, model one. What we should see is an FXT file that has the nominal values. So if I come back here, text file back, the nominal values that were specified. So for example, the EMOD nominal value is 1.13 e to the 6 pascals, the damping ratio 0.07, etc. So we can see that we're updating, or we're driving through changes to the FXT file from HyperStudy. The next model that we'll set up is the model for running the tire inflation. So that's an EDEM model. After adding the EDEM model, we'll go in and take the inflation EDEM file. We can go ahead and import the variables. Now in this case, we don't need to pull in any of the parameters from EDEM. So I'm going to deselect everything, collapse everything up, and click import. So in this case, we have no additional parameters to pull in. However, we do need to bring in a couple of additional files for the execution of Model 2. We'll take in the file, the FXT file. So in that case, we need to, in Model 1, add a output file, and we'll select the FXT file. And in Model 2, we'll add a linked resource, which will be the FXT file coming from Model 1. We will also need to add the input file FlexTire coming from our root directory, and we'll need to set that to copy. And we'll add in for the inflation, the EDEM pi post. Copy that. You can close this. Before I proceed, I'll just come back to the import. I didn't show this or mention this already, but I've already set up my profile so that it's set to run locally. That means it'll run locally on my computer. And within local, I'm going to change the output Python script to be run at the end of the EDEM execution to edem_post.py. And I'm also going to adjust the directory in which I'm using the Python executable. So in this case, I set up a virtual environment. I set up a virtual environment, and I'll point to that Python executable. Now I'll add in here a link to a video that will demonstrate how you can set up your own virtual environment to leverage EDEM pi and the post-processing capabilities. So I'll click OK, close this, and now we're ready to proceed through and write Model 2. And I'm actually going to come back here into the setup and change this to tire inflation. So if we look in Model 2, what we should see is the FXT file that has our nominal values. Yes. We need our FlexTire file. Now our FlexTire file, similar to the FXT file, it has a header that I would expect you wouldn't have to change. You have some input unit block here. These units are what the inputs are interpreted as in the file. So in this case, for example, in location, I'm specifying that the tire is located at 00, 1260 millimeters in the Z, so XYZ. And let's just open up our EDEM simulation that's in this directory and verify that, in fact, we have the appropriate tire in here. So tractor tire, you can see here that I've manually updated the center of mass to 00, 1260. Note if you include that auto calculation, the center of mass will be interpreted from the triangular elements of the tire, but it will perhaps be slightly off. That 1260 is coming directly from the original step file of the tire and how it was pre-processed with the STP to OBJ file from Pratt & Miller. I've also updated the mass. So again, this is the second location where you have to define the mass. The mass in EDEM needs to be specified as well as the mass in the FXT file. And note in this case, there's no particles. The simulation is being run just to quantify how much the tire is inflating. And note in this case that we're using a relatively large time step of 0.02 seconds and only running to 0.8 seconds. And we're simply using a CPU solver with 4 CPUs. So that looks all appropriate. I'll go ahead and close this. Oh, one more thing I wanted to point out here. We also need to specify the pressure in 2 locations. So if we go back to geometry, FlexTire, this is how we're enabling the FlexTire model, and we're pointing to the tractor_tire.flextire that's located within the m_2 folder. Note that for a relative path, we have to specify the folder in which the FlexTire file is located. Also note here that I've specified the pressure in 2 locations, once in the EDEM GUI here, 110,316 pascals, approximately 16 psi. That's also input in the FXT file. I'm going to go ahead and close this. So that model is ready to run. We can go ahead and execute. So this model is completed. We can open up the plot that was generated by the EDEM post Python script. And here you can see tire inflated radius starting off at 870, ending somewhere just above 920 millimeters, blue line. And the growth rate is also plotted here in the red dashed line, maxing out at approximately 0.1 second, and then dropping down to a threshold of below 5.0 millimeter per second growth rate at just after 0.3 seconds. The other output that's generated from this model is CSV output generated directly from EDEM's output. So we have the tire min and max X radius as a function of time. And we also have the output, the final radius, and a third output, the threshold time at 0.34 seconds that the tire radial growth dropped below 5 millimeters per second. So now we'll add in the data output responses. So we'll add in our data sources first. The first data source that we'll add in, I'm going to call it inflation time, and I'll give it a variable INFT. And this is going to come from our output here, model 2, threshold time output. We'll take the value of time. We will add in another response, inflated radius. And for this, we will look at final inflated tire radius, also coming from model 2. Now in this case, we're looking at an ASCII input, so I will use this keyword search that and give a length of 9 characters. And then let's also add in a couple data responses. Look at inflation time value, and for this, I'm simply going to point to the 0th index of the data source value And also I'll add an inflated radius. I'm going to leave that as R2 and taking the 0th value. So if I evaluate this, we can see that our inflation time in seconds was brought in at 0.34 seconds, and our inflated tire radius is 926 millimeters. Note that that's in millimeters. So our next step will be to go back to defining the models and adding yet one more EDEM model. This is going to be for the force deflection or deformation. Just model 3. In this case, I'll pull the loaded radius EDEM file. And now for this case, there are a few parameters that I want to include or bring in from EDEM in the simulation. First off, I'm going to adjust the motion that's associated with a tractor tire, and specifically the start time. We'll set the start time equal to the tire inflated radius time, or the time it takes for the tire to inflate to that rate of less than 5 millimeters per second. Similarly, for the simulation, I want to also export or control the total time. And I will also, within the geometry and the floor, pass in a transformation in the Z direction. So those are the 3 inputs that we need. Export to hyperstudy. And now in this case, you can see that we've got the parameters that are coming in from model 3. Note that to pass in the transformation in the Z, we do have to pass the full data set of XYZ rotation, XY and XY translation. Though we'll leave those deactivated, so those will all get passed to 0, or passed as values of 0. What we want to do here is link these or set these parameters up in this second EDEM simulation such that they're dependent on the first. And to do this, so here I think it's useful to switch over to the links. And for the links, the geometry Z transformation, slide this over so we can read it. In here, I'm going to paste an equation. Now this equation is taking into account that the tire is offset 1250. Now I'm just going to verify that if we come back to the FXT file, sorry, the FlexTire file, we can see that the offset is 1260. So that value should actually be 1260. So our tire is originally 1260 millimeters in the Z direction. I'm going to subtract from that R2. R2 is the radius of the tire, and in this case I want to have 100 millimeter offset, because if we open up the simulation, let me come back here, the loaded radius. Let's open up this simulation. See the way that I've defined the floor. It's a box that in the Z direction is 200 millimeters. So there's 100 millimeter offset between the surface of the box and the centroid of the box. So I'm adding in this 100 millimeter offset, and I'm adding in yet another 20 millimeter offset. That 20 millimeters you could think of as a buffer between the tire, the inflated tire radius, and where I want the floor to be positioned. I'm dividing all of that by 1,000 because EDEM is expecting an input of meters, and here I'm working in millimeters. So we can click on the 3 dots and verify that we should get an offset of 0.213 millimeters. Currently, the offset of the floor and the transformation is set to 0. So we can click OK. The next thing that we want to adjust is the downward start time. For this, I'm going to set that equal to the inflation time. That should be approximately 0.34 seconds. And finally, for the simulation total time, I want to run the simulation such that I generate 150 millimeters of deformation in the tire. So the units of 170 in meters, or 0.17 in meters, 170 millimeters, and the travel speed of the downward motion of the tire is 0.1 meter per second or 100 millimeters per second. Now, if I want 150, why do I have 170 here? Keep in mind that I've added in a 20 millimeter offset up here. So in total, I want the transformation of the tire in the Z direction to be 170 millimeters. And this means that the simulation must run for 2.04 seconds. So we can go ahead and save this. Right, and before I execute, I'll come back up into Model 3. And within Model 3, I'll open up the EDEM simulation and verify that we have the appropriate floor offset. So geometry floor transform. You can see here that I don't have the right transform. There's an issue that I need to address. Here I see that issue. I really didn't want to pass in a geometry file. And let's also, while we're back here, update the inputs that we need for Model 3. We will have to add in the linked resource from Model 1, the FXT. We'll add in the input file, FlexTire. And that needs to be set to copy. We'll also add in the measured tire loaded radius. That would be your reference data that has the tire force deformation information in it. Set that to copy. And finally, we'll pull in the EDEM post, different Python post processing for this model. Copy that. Close this. Let's give this another shot. Selecting delete. Yeah, this is looking more promising. So we can see now we have the EDEMPy post. We've copied in the measured tire loaded radius, and we have the two required FXT and FlexTire files in the same directory. We can go ahead and open up this EDEM simulation and verify that the geometry transformation has been implemented. Perfect. So in here we have 213.36 millimeters, the transformation of the box. We also have the tire downward motion set to start at 0.34 seconds, traveling at 0.1 meter per second down in the negative Z direction. And that's happening until the end of the simulation. The motion is set to continue till 999 seconds. And finally, our simulation end time, total time, has been updated to 2.04 seconds. Perfect. We can close this. We can proceed to execute. So our third model has completed, and we can see that there are a series of plots that were generated in our output file. First one I'm brought up here is tire force versus deflection plot. In the blue line, we have the tire force in newtons as a function of tire deflection in meters reported from the simulation that was just complete. The green dots, that data set is coming from the measured tire loaded radius, and the dashed orange line is the polynomial fit, third order to that measured data. And here what we're showing is the goodness of fit of the simulation to our target. Ideally, we want to have the blue line right on the orange line. The other plots that we have In the output, our tire patch area in meters versus time. Now, note that this tire patch area is a simplified approximation of what the tire patch area is, assuming it to be a rectangle, and I would expect that the tire patch area is in fact more of an oblong shape, so this would be a slight overestimation of what the tire patch area would be as a function of time. Now, finally, the plot that is also generated is the forces versus time in the other directions, not in the z direction, but the x and y. So x is in the direction of travel. You can see here that we get up to 1,750 newtons of force in the x direction, and the y, the lateral direction, stays relatively low or consistent in the range of less than 250 newtons. We also get some other important output information here that we will leverage. We have this CSV file that contains all of the information that's used to generate the plots that I just showed. We have time. That time data set is starting when the tire first touches the particle bed. We have the approximation for the simulation of the tire patch area in square meters, the tire deflection in meters, the XY forces, Z force, so that's the vertical force, and here the fit to measured equivalent force. This is the force that would be required by solving the fourth order polynomial with the coefficients specified here. We've got the r squared value of that polynomial coefficient, and also we have the initial tire radius specified here. So now we're ready to update our data sources, and for this we will add in a new data source, and we'll point to that CSV file, tire average deflection, patch area, and the first data set that I want to bring in is the time series. Go ahead and update the name of this to time. I'm going to set the variable name to the same. We'll add yet another variable, and just for simplicity or for fewer mouse clicks, I'm going to copy and paste that file path in, click on the three dots. Now in this case, I'm going to take the sim_z force tared, and I will update the name of this. The variable name, we will add in one more curve. Here we want to pull in our fit to measured equivalent, our reference curve, curve measured, and finally I will add in, I'm just going to remove this, three dots, area, and in this case, for the way that the area is calculated, we're going to use for the x, the time data set, and our reference curve is our sim force, our target curve is the time, and our fit to measured. So here you can see that the area between those two curves is 0.026. You can adjust the upper and lower bounds, but in this case it's not required. And alternatively, you can toggle this up here to plot the area to show the difference between the two. But those two show your two curves that we will ultimately want to set up and minimize the error between the two. So I'm just going to call this area between the curves, call the variable name area, and let's go ahead and specify a goal. We'll add a goal because eventually we're going to optimize. And what we want to do is minimize the area between those two curves. Go ahead and save the model. And we'll also add in one more output response. In this case, we'll call this area. And from our data source, we'll set this to the 0th value of area, evaluate that. Here we're passing through the area between those two curves. So now we're ready to continue on and set up a DOE. To accomplish this, we'll right-click and add, set a DOE, and we'll reference our setup. So that's just copying through all of the specifications that we've already set up for the model. D-optimal, we want to do a little bit of screening to figure out what parameters to include in the model. So I'd leave this as default, run 26 iterations. So what this is going to do, the objective here is twofold. First, we want to identify which of these input parameters has the most influence on minimizing the area between the two curves, the area between the two curves being the simulated virtual tire Z force response versus the reference data set. And secondly, we want to verify that the design space that I've specified here with the upper and lower bounds are such that the response that we get for the tire force deformation curve from the simulation encompasses our target or has a force response that's greater than and less than the target if you were looking at the tire force versus deflection curves. So we'll go ahead and evaluate this D-optimal by hitting apply and evaluate task. Now in this case I've set it up to complete multi-execution, 2 simulations in parallel. So our screening DOE has completed. Again, we're doing a D-optimal with 26 runs. And it's helpful here to take a look at the Pareto plot and look at the area between the simulation and the fit model. I've somewhat arbitrarily set the threshold, the contribution datum to 72% to identify that these 5 parameters, the material inner liner E modulus, material inner liner thickness, material sidewall thickness, material belt E mod, and material E mod, are the parameters that we want to include for the optimization. And perhaps you want to increase or decrease this, but the Pareto plot is giving us the approximate influence of the input parameters on the response. So the next step here is to verify that for the output response that we got, the response of the simulated tire fully encompasses the measured response. For this here, I'm looking at the curves that were generated. Here's an example of one curve from the iteration that was completed where our blue line is well below our orange dashed line, and then our second curve, blue line above our orange dashed curve. So we can conclude from this that the design space that we're exploring is sufficient. And our next step is to identify the input parameters that result in the closest match between the blue line and the orange line. And for this, we'll set up an optimization, add an optimization, and we'll set that from DOE 1. Now here, what we will do is adjust the parameters so that only the most influential parameters are included. In this case, I'll deselect all of the input parameters. We'll keep the linked parameters in. Those are required for the setup of the model, but we want the material inner liner EMOD, the material inner liner thickness, the sidewall thickness, the material belt EMOD, and the material EMOD. So we're disabling the Poisson ratio, the damping ratio, material inner liner, Poisson for the belt, thickness of the belt, sidewall EMOD, and the Poisson ratio for the sidewall. And for the optimization, we can proceed through to the specification. We have our goal set up to minimize the area between the curves. And for this, I would suggest that we use the global response search method, and we can leave everything as default. Hit apply and evaluate the tasks. The optimization is completed. You can see here that in total 50 runs were complete. If you take a look at the iteration plot, you can see that the area between sim and fit is generally driven down to a minimum threshold. And then if we take a look at the post-processing and under goal or the area tire, sort down, you can see that the best iteration was number 40 with the input parameters specified. So for example here, E modulus at 2.8, E to the 6 pascals, etc. The rest of the input parameters. So now that we've identified the optimum parameters, let's take a look at what that force deformation response looks like. And here's what that curve looks like. So it's a relatively good fit. Our blue line isn't exactly on the orange line, but relatively close. So now that we've verified the optimum input parameters to match the force deformation response, our next step will be to go on and calibrate the rolling resistance. So here we'll set up another optimization, and we can define that from the original setup, but we're actually going to modify the workflow here. For optimization 2, where we're optimizing rolling resistance, we'll actually remove model 2 and model 3 and model 2 will update to rolling resistance. Here we'll point to the rolling resistance file. And for the rolling resistance inputs, we're really only going to be adjusting the damping ratio, so there's no parameters that we need to bring in. And in this case, we really only want to be left with the damping ratio enabled, and we'll explore from 0.06 to 0.2. We'll have to update our model resources so we can remove some of this inflation, remove we appropriately have the link of the FXT file, we have the FlexTire, but we will want to add in the post-processing script, EDEM post for the rolling resistance, and set this to copy. You can go ahead and close this and verify that we get the appropriate input in our model study directory, and in this case we will go to approaches optimum 2 definition, model 2. Here we have the rolling resistance FlexTire. What we will want to verify though is that we have the appropriate inputs set to our nominal value from our optimization. So here I've updated the parameters, the nominal parameters to the optimum from our optimization one. Again, the only parameter here that we're changing is the rolling resistance. So we can go ahead and execute this first model. Right, to verify that those parameters have been driven into the FXT file and execute. So the setup model has run to completion, and we can switch over to the study directory, and you can see that the output file generated from the EDEM post includes a plot that shows the force in newtons as a function of time in the X, Y, and Z direction. So X is in the direction of travel in blue, green curve is the Y, the lateral direction, and Z, the vertical force. In this case, you can see that I've got a force controller that is approximating 10 kilonewton vertical load, and the motion of the tire is starting here at approximately 1.3 seconds. And we have some variation in the vertical force. Likely that's from the lugs, the roughness of the tire. And finally, the rolling resistance in purple is a unitless parameter right off the right side. So you can see that generally the rolling resistance follows that same profile as the X direction and the vertical force. Beyond that, we also have this tractor tire processed tire forces file. If we open this up, we can see that the information has been extracted from the PM solver. We have the XYZ forces and a steady state rolling resistance and the rolling resistance. So if we come down here, the rolling resistance calculation starts when the force is non-zero and goes to the completion of the run, and this last steady state rolling resistance is just the average of the rolling resistance. So what we want to do is bring that parameter in. We won't save that. And to do this, we will go in here and add in a new data source. And this data source will be from model 2, our processed tire force. Ultimately, what we are after here is the steady state rolling resistance. RR. And we'll go into define output responses. We'll add another output response. In this case, we will take the 0th element of this guy. Again, we won't leverage the outputs here. They're not applicable for this, this investigation. So as you can see here, we've pulled in from our text file the steady state rolling resistance for this damping ratio. Now the next thing, I'm just going to come back here and update the output response, steady state rolling resistance, switch back to goals, and we can disable the data sources that we will not be using. Setting this up, I'm going to add in a another output response and call this the target rolling resistance. And the target rolling resistance in this case, I'm going to set to 0.1. Evaluate that, and we'll add yet one more response. resistance air. And here I'm going to take our variables, output responses, take our target, subtract our steady state, and square that difference. So that's the error between our target and actual. Evaluate, and here we have the rolling resistance error. We want to come here and set the rolling resistance to our what we're going to operate on, and we want to set that to minimum. So here I'm just going to update the target to 0.05 for the target rolling resistance, so it's just slightly higher than what our original rolling resistance was of 0.036. We've set that up, so we're now ready to set up the optimization. In this case, I'm going to use the global search response method. In this case, because we've only got one variable, I think it's reasonable to greatly reduce the number of evaluations. Something like down to 5 will be plenty for this application. So I'll apply and go ahead and evaluate the task. The optimization is run to completion. 5 iterations were completed. Here we can see on the evaluation data tab that for a material damping ratio of 0.13, we get the closest to our target of 0.052. You can also take a look at the evaluation scatter, comparing steady state rolling resistance versus damping ratio, and you can see that generally there's a direct relationship between the two, and the closest iteration that was run was at that 0.013. So that is how you completely calibrate the rolling resistance and the force deformation of the PM FlexTire.